Module 2.5, Helmholtz Resonators. Get ready for an exciting moment. Drum roll, please. We are about to learn about something that actually has to do with sound. Have you ever held a seashell up to your ear? Have you ever blown across the top of a soda bottle? Have you ever knocked on an acoustic guitar body? Have you ever played an ocarina? If so, you've actually confronted a Helmholtz resonator. A Helmholtz resonator is nothing more than a hollow object that has an opening. And yes, you've guessed it, there's a formula for finding the frequency of a Helmholtz resonator. It is F equals V over 2 pi times the square root of A over VL. F equals frequency. Small v equals the speed of sound. A equals the area of the opening. L is the length of the neck. And big V is the volume of the resonator. Now, if you look at this, you should see that it is similar to the formulas for a pendulum and a spring mass system, but it has more variables. Even so, a Helmholtz resonator is a system that exhibits simple harmonic motion. Let's take a look at how this happens when blowing across a bottle. As you probably know, gas is easily compressed. As you blow, the changing airflow coming from your mouth pushes down on the air in the neck of the bottle. That presses down on the air inside the bottle, which is then compressed. Being compressed, it then pushes back up. That pushes the air in the neck out of the bottle, and if you are still blowing, the air in the neck goes back down, repeating the pattern. You can think of the air in the bottle as a spring and the air in the neck as a mass. So a Helmholtz resonator acts essentially like a spring mass system. So let's look at the big picture. F is directly proportional to the speed of sound and area. So as the speed of sound or the area of the opening increase, frequency increases. F is inversely proportional to volume and length. So if either the volume or the length of the neck increase, frequency decreases. If you remember the demonstration on the first day of class, this now explains why the two soda bottles were the same pitch and why the wine bottle was lower in pitch than the soda bottle. We'll do the calculations to show that in the lab. Also, as with the spring mass and pendulum, since area, length, and volume are inside the square root sign, it's a square root relationship. Now, let's take a little trip to the real world. The seltzer bottle quandary. I take a 1-liter seltzer bottle. With a ruler, I measure the diameter of the opening and the length of the neck, and I get 2 centimeters for the diameter and 3 centimeters for the length. I use pi r squared to find the area of the opening. Doing some math, I get frequency equals 176 hertz. That's the note F. So I blow into the bottle, and what comes out? 145 hertz. That's the note D, not even close. Here's the bottle pitch. Now here's what 176 hertz sounds like. What happened? First, it turns out that a 1-liter bottle of soda has a larger volume than 1 liter. Actually, it's about 1.04 liters. So a larger volume would lower the frequency. But it turns out it only lowers it a bit, to 173 hertz. It turns out the classic Helmholtz resonator equation assumes that the air in the neck is a solid. But in actuality, because it's a gas, the air above and below the neck actually contribute to the mass. So to compensate, it's necessary to add a fudge factor of 1.5 times the radius to the length of the neck to give us the effective length, or L sub E. Once we do that, the calculated frequency becomes 141 Hz, a much better result. So the true formula is F equals V over 2 pi times the square root of A over V times L sub E, where L sub E, the effective length, is the length plus 1.5 times the radius. In the lab, we will use the effective length so that our calculations will predict the actual outcome. However, if I say ignore effective length, you may use the simpler formula. To review, a Helmholtz resonator is a hollow object that has an opening. Frequency equals velocity over 2 pi times the square root of area over the volume times the length. Frequency is directly proportional to the speed of sound and the area. Frequency is inversely proportional to volume and length. To get an accurate calculation, change length to effective length, which equals the length plus 1.5 times the radius.